Thank you, everyone, for being here at the search track for ApacheCon Home 2021. For anyone who's been involved in Lucene, speaker Uwe needs no introduction. He's a committer and C member of the Apache Lucene and Solr projects and a bunch of other involved in a bunch of open source projects. So with the focus on Java Lucene. He invented the fast numeric search and a lot of other things that would take me a really long time to mention. Uwe works as the managing director for SD Data Solutions in Bremen, Germany, a company that provides consulting and support for Apache Lucene, Solr, and Elasticsearch. He's an active speaker at various international conferences and local meetups. Today, he'll be talking to us about the future of Lucene MMapDirectory, why use it, and what's coming with Java 16, 17 later. Over to you, Uwe.
Yeah, hi. So I don't think I need to show that slide because thank you for the brief or longer introduction, and I will directly start with the interesting stuff. And I hope the time is enough. So questions are not allowed today. No, that's a joke, but you can send your questions. So I will start with memory mapping. So I wrote a blog post about that already in 2012. And here I will bring a brief overview why Lucene is using memory mapping for accessing index files and why it is better than conventional I/O. So I'm starting with that slide here. To everybody who was in the early days of Unix knows those type of code. I call it the 70s style of file read. So in the 70s, you were reading a file like that. So in C code, this is not even Java code, Java didn't exist here. You had two functions more or less. After opening the file, you were able to seek to a specific position in the file using the file descriptor and some offset, which is the first one of those functions. And the second function is then to ask the kernel to read a specific amount of data, which is here notified as count, into a buffer that is inside your process. So that means there's also copying included, and you have to seek before. The problems with that is you have to allocate a buffer in your local program, and actually you have to do two syscalls. So that means you have to transition 2 times to the operating system kernel, 1 time to seek to the file position, and the second time to read the data and copy the data to the local buffer, because the kernel just reads it into his private address space, and when it hands over it to you, it needs to copy the stuff to your local buffer. And the workflow behind the scenes here is the kernel reads that from the disk in its own file system cache and then copies it over from the kernel space where the file system cache is inside to the user space over the border. There's this nice picture how the file system cache generally works. So basically it's saving not really files like in the picture, it's blocks of slices of the files are saved in the memory controlled by the Linux kernel. And if some process requests it, it is handed over. And also, if you want to allocate memory to work in, then it's basically the same. It also allocates a little bit of disk space. And if there's not enough, in this case, memory space, if there's not enough memory available, it just frees up cache space. So basically, that's how the file system cache works. We come back to that a little bit later because this is just a very, very simplistic view of it. So the problem is that seek, copy, and so on for Apache Lucene is that it gets worse if you are working with Java like Lucene is doing, because as said before, you have to allocate a buffer in your process, but actually in Java it's a little bit more because of the garbage collector. You need to allocate a local buffer in your heap, and that is where the application works on. So basically there's one more copy operation included. So actually you copy the data from the file system buffer in the kernel to something which is called a direct buffer, which is allocated by the JVM, and then the direct buffer is copied over to the byte array that you're using in your program, like in Lucene. In Apache Lucene, this is implemented by the simple fs directory, which also uses the seek-based access. And there's another problem with that approaches, and that's caused by multithreading. So we see here we only have one file descriptor per index file in Lucene. If we would have one per query or whatever, for each thread a separate file descriptor, then we would run out of file descriptors very, very soon. And the problem is, you know, we had two methods there, and two functions to call, the seeking and the reading. And if you seek first and then read some stuff, you have to somehow synchronize that, because otherwise another thread could seek somewhere in the file, and then it handles over to another thread, and then it reads the wrong stuff. So you need to have a synchronization around it. And that's a problem with Lucene, which is heavily multi-threaded. So simple fs directory is something you should only use as a last resort in your code, because every access to the file system needs to be synchronized. To get around that a little bit, I call that the 90s style of file reads. You move both together to a single system call, which is a positional read. And that is looking like that. You have a buffer and you have a count. You want to read a certain amount of data from a specific offset in the file. So you here combining both the seeking and the reading into the same into the same syscall. So that removes the need for the synchronization, because each thread has its own offset where it reads from, and there's no concurrency problem. So in Lucene, the implementation for that is a new IOFS directory, and the new IOFS directory also has another good thing included, because it's using the new IO interface of the Java. It prevents, in most cases, the duplicate copy, because you can have native access to the direct buffer, which is located outside of the heap. So you don't need to always copy the stuff over from the direct from this internal direct buffer, because you can directly go to the direct buffer and read your stuff in it. And this is a good thing for Lucene in some cases, but there are still the problems. Like you have to read the whole stuff in chunks, because whenever you want to access something on disk, you have to do a syscall. So you want to spare syscalls, because you need to have a transition to the kernel and back. You have to do all this copy stuff. And because of that, what you're doing is you're copying something like a larger block of data into that internal JVM direct buffer that you're working with. And the second problem that we have with that is it doesn't work on Windows. Because on Windows, implementation in Java is not fully correct, so it does not allow to do real positional read. So internally, it emulates them by the old seek and read, which needs a synchronization. So when you're using simple fs directory on Windows, you are when you're using UIOFS directory in Windows, it's as bad as simple fs directory, and it gets even worse. So that's just a warning for everybody using on Windows, because there was a question already how to deal with Windows. So the questions now, when looking at those two APIs from the 70s and from the 90s, is why do we copy all that data? Why do we do that? Why do we need to do copying 3 times? Because we know from the very, very first slide is, we know all the data is already in the file system cache. So it's already in memory. We just copy it over to our Java process space for no reason. And we must do that in bulks, which makes no sense. And why do I need to ask the kernel every time that I want to read a specific piece of file to my local space? Why do I need to do that? And the solution for that is now the Millennium style of file reads. You read correctly. It exists since the early Millennium style, so it was already available in the 90s. But still up to today, a lot of programs are using the good old read, seek, APIs instead of using memory mapping. So Lucene in, I think, 2000, from the early beginning, I think 2007, 2008, offered the memory mapping for that. The idea here is to prevent the copy of data between the buffers, OS kernel, user space, Java heap. And the second thing is it doesn't need to do any syscalls at all. And it uses EDLFS. The file system cache is used in an ideal way. And if you would think of, I will explain now how it works. It's also simple code, theoretically. But unfortunately, in Java, it's a little bit more complicated. And this is why we have this talk at all. So what's going on with memory mapping? We have something that is called the so-called virtual address space. So basically in modern operating systems like Linux, but also in Windows or FreeBSD, whatever, Solaris, actually no program really deals with hardware physical addresses. So it doesn't say, I want to read from that memory chip, that amount of memory. Nobody is doing that. What happens is every operating system process, so for example, your Java virtual machine gets its own virtual address space where it can do whatever it wants. And it can only access exactly that virtual address space. There's no way to access outside memory. And the trick here now is to map that virtual address space, which can consist of several spaces, to your real physical memory. So that's just something like a virtualization behind. So it could be physical memory, or there could also be on the physical memory something like other processes memory. So there's also a possibility to share data with other processes. That's another issue. And the cool thing with that is you could also map virtual memory to disk space or your SSD. We just call it disks here, and that's the idea. But how does that work? And the technique behind that is called paging. And basically what happens here is on the left side, the red CPU box, for example, you have in your process, in the Java process, you want to access some virtual address, which is starting at 0. So your process starts at address 0 and goes, has a large virtual address array. So it wants to access a specific address here, 1, 2, 3, 4, 5, 6. And then there's some chip inside the CPU, which is called the memory mapping unit. And this one has a small cache, which is called translation look-aside buffer. And this one has, for the most commonly used addresses, a direct mapping to your main memory. And that's, if you have a hit in that one, it can directly translate that. This is here in the 2A to the name 987654 address, which is here on the top left in our main memory. That's the first step, which is the fastest access possible, so we can access it. There's also a possibility that the cache does not know about that address yet. And in that case, there's a 2B route, which is then handing over to your operating system kernel. So processor says, I have no idea where that address is. I ask the operating system, so it hands over to the operating system. And the operating system has somewhere else in memory a huge table of all processes available that are running in the Linux kernel. And then it can do a slow lookup in the table and say, okay, I know where that page is. So I have a page hit, and then it can also go to the same page. And as a side note, it would also silently update the translation look-aside buffer. So when the CPU accesses a similar address soon again, it would not go through the page table. But there may also be the possibility that the page table contains an entry. No, there's no memory available for that one. And there are two possible things. The first one could be the memory address is not mapped at all to something. That can happen if you have an error in your program and go far outside of your memory. And then in that case, it's going somewhere. And the page table does not have an entry. And in that case, the Linux kernel will cause a segmentation fault in your program. That's the famous one when your program crashes and this segmentation fault is appearing. That is what happens. But if the kernel knows in the page table, this address is mapped to something which is on secondary storage, like in your swap file of your operating system. So you know here it's a swap file is managed by the same address, or it is mapped using memory mapping to a file like the Lucene index on disk. Then the following happens. It then copies over the operating system the data from the secondary storage like the SSD to the main memory. Sometimes this is called a page swap. For example, if it's swap files, you have to, of course, preserve the stuff which is currently in memory, write it to disk. But if it's read-only like a Lucene index, you just have to copy the stuff over. So in that case, it just copies the stuff to your main memory. And then the same happens. You're updating the memory mapping unit, the transaction looker side buffer in the CPU can read that memory address. So basically that's how virtual address space works. So the trick here is for the Lucene indexes, whenever we access something in your Lucene indexes which is not yet in memory, the operating system kernel will take care of mapping it into our virtual address space. So we don't need any program logic. The only thing where you can help the kernel a little bit is to add more physical memory to your hardware, so it has more space to place all those mapped in paged slices of disk space into your main memory. So if you give it more memory, it does not need to page too often, so it can in most cases simply tell, here is a memory, just go to the pointer and then you can access it using that virtual address. So that's the most important thing, is give as most as possible physical memory to your Linux machine running Elasticsearch, Solr, or Lucene. So how does it work in Apache Lucene? So Apache Lucene and memory mapping works using the MMapDirectory abstraction, which is by default used for all 64-bit operating systems. And this one has an index output and index input. Index output is shared by all the disk I/O stuff, because this is just a standard output stream where we are writing our index to. But for reading, we're using an index input, which is called, which is based on mapped byte buffers, which are mapped into the virtual memory in 1 GB size chunks. And the mapped byte buffer, you may know that class, it's a subclass of byte buffer, allows access to any pointers they are using random access. You can go directly to a virtual memory address, read it, and do something with it. But you can also, of course, do sequential access. So the question is now, why do we have those chunks of 1 GB? That's a little bit of a workaround for a problem that exists in the early days of Java, and now we come to the complicated parts. The problem is Java's byte buffer is 32 bits only. And the problem with the 32 bits, it's signed. So that means a buffer can only go from address 0 to the address of 2 GB minus 1. That's a problem. The buffer's size must be 1 smaller than 2 GB. So that's the bad thing with signed pointers that are 32 bits. So for efficiency in Lucene, we want to do the access to the buffers easily as possible. So for example, to find the correct byte buffer for accessing the correct space of virtual memory, we just want to use the bit shift and the bit mask to get as fast as possible to the correct address. And to do that, we have to limit ourselves to 1 GB because of that stupid -1 issue on top. We can only go to at a maximum 1 GB, and that's a reason for the 1 GB chunk size. So if you look at the code of memory mapped directory, basically for performance reasons, we don't do any calculations. We do some calculations up front, but we try to do our best to simply get to the right pointer. So that means here in that case, we are just doing a bit shift, and then we are reading from the byte buffer. We don't do any bounce checks. We leave that over for the Java APIs of the byte buffer. So, for example, if we are executing out of bounds, we are just converting that to an EOF exception. So if you're going beyond the buffer, we just stop it. So, but this only works if the byte we are reading is inside those buffers. Otherwise, you get one of those exceptions. Yeah. So the problem is now if we have many buffers here, so we need to have some logic to get the right buffer. And sometimes we not only want to read a single byte. A single byte you can always read, but there's a problem. For example, if you have an integer which is 4 bytes, shortly before the end of the first buffer, and you read it. So in that case, you would the first buffer only has 3 bytes left, so we cannot read 4 bytes at all. And in that case, we get an exception. And now here we have some try-catch programming logic. Don't show that anybody. This is really horrible programming style. But you know, our buffers are 1 gigabyte of size. So it's very, 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 very seldom that we are just reading an int at the end of one buffer where we need to switch to another buffer. So in that case, we say we don't care about the exception. If the exception happens, we just fall back to our old code and read byte by byte. And that code is then handling our transition from one buffer to the next buffer automatically, also through that logic. So basically, in most cases, it simply works. And if it does not work, we get an exception. We just transition to another buffer. So that's the important thing about the Lucene byte buffer. You have to keep that in mind because if you read that code, a lot of people say this code is so horrible. Exceptions cost so much if you hit them, but this is not really true because it's very, 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 very seldom. Even with 1 gigabyte, it's very seldom that this happens. The same, by the way, also happens if you're reading a sequence of bytes, not only if you read an integer. The same happens. We try to first read the whole buffer, and if it doesn't work, we split it up into several buffers. So there's something more in the Lucene about the I/O characteristics, which makes it easy for us to use memory mapped I/O. All files in an index are write once and read many. So we never write to the same file on updates of the index. Whenever you have updates in an index, we create a new file or a new segment. For deletes is sometimes a new file, so we write to new files. A file which was written to disk by the Lucene index using the output stream, as said before, never changes anymore. So in that case, we know for sure once we have memory mapped the file, it won't change anymore. So we don't need to take care of maybe file size changes. We have to remap or something like that. So we don't need that. We just assume the file is open and we can access it and it doesn't change. So when we have highly concurrent access to the whole thing, the code is using duplicate byte buffers. And for the duplicate byte buffers, we don't need any synchronization because nothing changes. We can just access them. So it's all without any synchronization, the code you have seen before. So, and here the problem starts because we have a huge problem since the early days. And you remember we have several threads. You have sometimes 100 of threads executing a query on the same segment in the same memory mapped area. Is there a way to close the file or unmap the data? You remember, if I'm doing an unmapping, what happens? The kernel, you know the picture before, the kernel just says, oh, there's no longer something mapped in that virtual address space. I will zigzag fault your program. So your Java machine would segmentation fault. And because of that, in the early days of Lucene, they just forbid, they don't offer an API to do that unmapping. So that means once you have memory mapped a buffer, it stays in the virtual address space forever until the garbage collector figures out that no program code is using the memory mapped area anymore. And because of that, we don't we don't see that freeing actually take place because Lucene index are often for hours, and it's only a very, very small byte buffer object pointing to something which is a gigabyte of memory outside, or gigabyte of a file outside of the heap space. So the garbage collector doesn't take care of it at all, so it won't free it. So there's no chance to unmap that buffer. And what we are doing here is we try to force that on our own with the risk in Lucene and also Solr and Elasticsearch to see that error message when you're accidentally closing your index while at the same time a query is running. Because what happens here, as I said, there's no synchronization. It could be that a query is still executing in another thread. Thread A unmaps our memory, and what happens is the address gets invalid, but the other thread doesn't notice of that address getting invalid and accesses that address, and the Linux kernel says, no, you can't do that. I will kill your process. And that's what happens. And because of that, we have to take care of that. So there's a 19-year-old feature request to solve that problem in Java. And it's up to today, it wasn't solved, and it won't never be solved for byte buffers. I can tell you that. For byte buffers, it will never be solved. There will be no close method for byte buffers. And what we are doing here is in Lucene, we know the risk and we take care. So Solr and Elasticsearch have very clever code with searchers and index readers to make sure that that you don't access a memory when it's unmapped. So what we're doing is we're going to private APIs in the Java class library to call that small piece of code, which is called normally only by the garbage collector, to unmap the memory from the Linux kernel once we are done with the byte buffer. So when we are closing an index, we just tell all the byte buffers that we have, close or unmap the memory behind. And since Java 9, this is done through sunmisc unsafe. Previously, you had to hack into the JVM at different places, so it was really a bit strange. So currently, we have a lot of code about that in Lucene, which makes sure to apply that workaround works in most of the JVMs that are supported. If it's not supported, MMapDirectory will not work for you. So it will tell you that no, that doesn't work. You can't use it. You can optionally use it with automatic unmapping, but then you will run out of space very, very soon. But all the new JVMs, except maybe for the old Apple JVM or whatever that existed till Java 6, they all know that now. So we can do that. So how to use MMapDirectory on all 64-bit platforms, it's enabled by default. So you just use fsdirectory.open. Elasticsearch and Opensearch use it by default for most index files. Elasticsearch has a small optimization because a lot of people, customers of Elasticsearch have many indexes, and there are some limitations in the operating system. So for some of the index files, they're using still the traditional I/O, and Solr adapts the standard Lucene factory. So if you look at your operating system, it mostly looks like that. That's also an important thing is when you're looking at that, there are two things, the red one and the green one. The residential memory is 7.6 gigabytes here, but you have a virtual memory of that Elasticsearch process. This is Elasticsearch here in that case, of approximately 74 gigabytes. And if you compare that with the output of your cut indexes and you sum that up, you are very, very close to that virtual address space. But actually, the virtual address space is just virtual. It doesn't consume any physical memory. The physical memory is somewhere here in the buffer and cache size on the top. So actually, if you have many indexes, it could also happen that virtual address space shows more than 1.5 terabytes. There's nothing that's wrong with that. It's perfectly fine. The only actual physical space used by Lucene is a residential disk space, the green one here, which is more or less your heap space and a little bit more. So the tuning, the most important thing for tuning about memory mapping is assign as less as possible JVM heap. So maximum is 25% of your physical RAM. Trust me. Don't do too much because Lucene works completely out of your heap space. So it depends. If you're using Solr and do a lot of faceting, you may need more physical RAM. But standard Lucene can do most of its stuff outside of the heap, all in that virtual mapped address space of your index. So that's the first thing that you need to keep in mind. So keep the residential memory low and leave as much as possible free for the file system cache. And then if you have many indexes, you also need to raise a maximum mapping count. The reason why you need to raise that is because of that stupid 1 GB limit, as I told you before, because we need all those mappings in multiplies of 1 GB. So you have you need for every gigabyte external memory map, you need 1 mapping. And another recommendation is to only run Lucene, Solr, or Elasticsearch on the node and nothing else. And if you have Windows, don't do that for huge indexes because of some internal problems of Windows and how it regulates the virtual address space. Everything larger than 1 terabyte is a mess with Windows. So now I'm coming to the project Panama, where the main part of the talk. So we have still 10 minutes. This is okay, I think. So not much questions. So Project Panama. Project Panama is something which came recently to the JDK. It's about improving and enriching the connection between the Java virtual machine and the well-defined but foreign non-Java APIs, including many interfaces that are commonly used by C programmers. So what does it mean? The key concept here is something which is also interesting for the Lucene. The first thing is we have so-called memory segments on top of memory address. Memory segment is more or less the same like the byte buffer that we have seen before. And the second thing is we have var handles, which is a new feature since Java 9. And the var handle is there to access that memory segments with different data types without any specific overhead, because it's all automatically compiled at runtime, so it gets the most ideal path, for example, to read an integer from a memory segment. The memory segment can cover any address space in the virtual area, so it can be on the heap, off heap, memory map. It's just like a byte buffer, but with with one change, it's using a long to access it. So actually, we can memory map now the whole index file that we have with a terabyte theoretically into one memory segment. This is fine. So the first thing was the project Panama in JDK 14. It arrived for the first time. The problem with that was we tried to use it with Lucene, but there's one problem in it. There's a so-called thread confinement. You know, the problem that I told you before, with multiple threads accessing the same memory segment, there's no possibility to unmap it easily without crashing your JVM. And to work around that, the easy solution for the first phase was, we make the memory segment thread confined. So only one thread can access it. So from Lucene's point of view, that would be, we open the file, memory map it into a new memory segment, execute a query. After the query, we unmap the segment, and then we do the whole thing inside try with resources. Of course, that's not how Lucene works. So there's no way to use that, because we have many threads. We want to have our stuff memory mapped in memory, and we want to access it from multiple threads at the same time. So JDK 14, we immediately stopped to look at that. So that was the first thing. In JDK 15, that was half a year later, there was now the possibility to allow to transfer the ownership of those memory segments to other threads. Yeah, so, and the possibility was also added to close the memory mapping. So the thread owning the memory segment was possible to close the thread. There was also the possibility to clone a memory segment and use it in a different thread, but only the one owning it was able to close it. The problem is in Lucene, we don't know who closes the fucking index. We don't know it because it couldn't be any thread simply closing the index. So again, no use with Lucene. And there was always the idea every year on the FOSDEM conference in Brussels in February. I was meeting with the OpenJDK guys like Mark Reinhold, and all the time there was a joke. Yeah, you have to spend a lot of beers to Mark Reinhold and ask him that he adds the unmap to byte buffers. That was always a joke. And now in the year JDK, after JDK 15, at the beginning of JDK 16, we were sitting together in the Oracle offices in Brussels, and we're discussing about that problem. And we were trying, we can't use that because the memory segment is a byte buffer that we can only use from one thread. So this doesn't help us for Lucene. So there was Andrew Haley at that point, it was already 2016, who had a good idea to have the thread confinement solution. And this came into JDK 16. So we have a shared memory segment, which has a close method to do it. And if other threads are using it, it has thrown an illegal state exception. Oh, that was really cool to have that. But how does it work? Yeah, you have to know a little bit. So the state after JDK 16 was now, we have no slowdown when accessing the memory segment. But when we are closing the memory segment, the trick now by the JDK is it, for a very, very short time, stops all the threads. It cleans all the caches. So no, and so it's something like, it's called a save point. And during that save point, we do our unmapping. And then all threads are started again, and and the whole thing works. And that's a trick now the JVM is using. So we have now no degradation of speed when accessing our memory in the memory segment area. But when one of the threads unmaps the Lucene index, for example, one file, all threads get stopped for a very, very short time, which is a so-called save point. Save points happen quite often in the JDK whenever something like an optimization in the program code has to be stopped from working. So it's not seldom that it happens. But you have to keep in mind, whenever you close and unmap our stuff, all threads get stopped for a short time. So now we had the first pull request. It passed all the tests. The code is very, very similar to the code that we have seen before. So we are using now var handles instead of those byte buffers to access bytes, shorts, ints, or longs. And the code also looks familiar. So we are using the variable handle to access it with the current segment that is working. So it's basically almost the same code. No much changes in it. And it worked perfectly. It worked perfectly. Now, we also changed the default chunk size to 16 gigabytes. And the reason for that 16 gigabytes was most index files will fit into those 16 gigabytes because of that limitation of standard limitation of 5 gigabytes per index segment in Lucene if you don't optimize your index. And this is a dramatic reduction by factor 16 of your mappings. So you can run more indexes on the same machine. So the address-based fragmentation is one reason why we have the 16 gigabytes, because if you map a file of 1 terabyte, at some point also your 64-bit address space gets chucked. So with JDK 17, that was released with Java 17 just 2 weeks ago. We had a little bit of performance improvements. You can look at the code. There's a new pull request for that. Memory segment uses auto-closable, and there's a new class resource scope, which allows us to unmap many segments at once, which is also something Lucene needs, because sometimes when we close an index, we have to close 10 files or something like that. So we can use the resource scope and have the short time to stop the whole JVM as short as possible. The pull request is 177. You can try it out. We figured out the var handle access is very, very fast, but bulk copies to Java arrays were still slow. And because of that, it's not usable. It's with JDK 17 because those bulk copies drive your garbage collector crazy. And now, hopefully, with Java JDK 18, we get the foreign API refresh, which cleans up a lot of that, and it also makes the bulk copies from and to the Lucene index, from this to the Lucene index much better. And this was already tested on that pull request. There's no public pull request in the Lucene repository yet, because this is not even committed to the JDK. So it was running on my own hand-compiled JDK. And I can confirm now everything works as expected. The speed is fine. And now the problem is, when can you use that? So JDK 18 is still incubating. So to use the whole stuff, you have to pass some crazy command line parameters to use it when you're compiling and when you're using it. And the current plans, you can see the web page on the bottom, is that possibly maybe already with JDK 18 or JDK 19, the whole Panama API will move to the JDK base module, and the packages will be Java lang invoke for the var handles and all that stuff, and Java lang foreign for the memory segments. And then we will have 2 JDK releases in so-called preview state. So preview state is a little bit better. You can use the APIs, but to use the APIs, you just have to pass a command line parameter, but there are no security issues anymore. So theoretically, with JDK 18 or 19, we could provide something for Lucene, which you can easily use. And as you might have heard, the next JDK long-term release will be JDK 21, which perfectly fits that time area. So in JDK 21, we will release it in long term. And then maybe Lucene 10 will by default use the project Panama. Up to there, I personally will provide the MMapDirectory version 2 jar file compiled for JDK 18 on GitHub. And then you can simply plug it into Solr or Elasticsearch or your Lucene code to try it out and use it, but that's not yet ready. I will do my best to do that. And once we have an idea and it's stable in the JDK, we will add it to Lucene, maybe as a multi-release jar file. And we also want to extend the whole thing a little bit more, because you learned you can also access low-level APIs in the Linux kernel. It may also be possible, for example, to log slices of files into memory and all that stuff. And we will combine it with the vector API to do some of the vector calculations in Lucene off heap. So that's all. 2 minutes late. I think questions are disallowed now, but you can grab a beer now for the next session. Do you have any questions? There are many questions. Uwe, what does your t-shirt say? The t-shirt says a programmer is somebody who is converting coffee to program code or something like that. Hi, Anshum. So the t-shirt is already explained.
Okay. Can you hear me? I switched my microphone.
Yeah, your microphone is a little bit bad, so maybe I answer the question on my own. I don't hear you.
You still can't hear me? You can't hear me still?
No, I can't hear you.
Okay, give me a minute. Can you hear me?
Is this better?
Yeah, not really better. So I see the questions on my own. So
okay.
Yeah. The question by Mike McCandles: Uwe, does JDK 17 also expands advanced effort-wise, MUD-wise flex or features? Yes, it has. So actually, I can show you some example slides here. Here you see the code, how you can use that. So we can use mlog2, for example, if you have a memory segment and a memory address. So you can do that. It's possible. Yes. So the problem is there's improvements needed for stuff needs to access file handlers.
Okay, Uwe, trying again. Can you hear me now? Is this better?
No, I can't hear you. I'm repeating my questions on my own.
Okay.
Is in memory mapping related code Lucene specific or can be extracted to other similar where reads or files? I think you can, of course, use that. So also inside Lucene, memory map directory is used for other stuff. Like, for example, Solr is using it for copying files over, so theoretically over the network. So it reads the file still from a directory and serves it. So theoretically, yes, you can use it. Memory mapping in that case. So basically, yes, you can do it. How much beer did it cost? I don't. Many beers, I think. So. Yeah, but the good thing is when you're meeting with Oracle, in most cases, Oracle pays automatically. Also, if you're spending beers to Mark Reinhold. That's a joke here. Yeah, no, no, but actually, it's a lot of discussions always on the FOSDEM conference. Unfortunately, this year there was no possibility to attend FOSDEM in person, so there was no Java room. So this year I had no possibility to talk to anybody in person. But the last year, the year before, so that was February 2020, shortly before the Corona started, I was shaking hands and we did everything to get the unmapping working with Project Panama. So actually, it worked with enough beers.
Where did you take the last question?
The last question is, you mentioned don't use memory mapping with Windows. There are multiple reasons. Not all of them are fully known, but the mapping in and out of Windows is behaving very, very bad. So it tries to memory map a lot of more stuff into memory that actually needed and you can't configure it. So it sometimes also memory maps stuff, and instead, when it memory maps, it on the other hand, it unmaps program code to the swap file. So the first thing is you have to disable your swap file on Windows to make use of it. And the second problem is the address space on Windows, at least with the long-term releases of Windows, Windows 8 and the corresponding mostly used long-term, I think server 2016, what's used in most cases. The problem is they have a very, very limited space, virtual address space. I think it's only 46 or 45 bits of the 64 bits, in contrast to Linux, where you can lose a lot of more virtual address space. So actually, the pointers cannot be 64 bits. They are smaller because they are somehow limited by the address bus of your hardware and also by the operating system kernel. That's the reason. So Windows is not working well with memory mapping for too large indexes because you may run into the usual swapping hell.
Okay, I think we need to wrap up. Are you going to be around? I guess you will be the next 2 days as well. Yeah, are you going to be around? I'm assuming you're going to be around the next 2 days.
I don't understand. I don't understand you. Unfortunately, I think you have to tell it in the chat.
Okay.
I need to wrap up. Yeah, okay. I think so. Hopefully you enjoyed the talk, and I'm looking forward to somehow maybe in the next year to present something that works with Lucene. Just stay tuned on the GitHub. Maybe we also release it with Lucene as a separate jar file, so you can plug it in and test it out. So hopefully with JDK 18, latest JDK 19, we will have something that can be used out of the box, I hope, with the same performance and less resources. And you won't see any segmentation faults in the future by code not using Lucene correctly. Yeah. Thank you. So you can still have any questions here, I think. That's already a question about what should be the ideal proportion between JVM heap and virtual memory. What I tell customers always is run your Solr or Elasticsearch server under high load and then try to reduce the JVM heap as much as possible until you see the first out of memory error, and then put half of it on top again, and then I think you're fine. Something like that. But the initial ratio is not there. So there are also some other rules. Never give more than 31 gigabytes of heap space to your JVM. So if you have a machine with 256 gigabytes, then it might still be possible to run your Lucene index with 8 gigabytes of heap space, but not more than 31 gigabytes, because the next step would be much larger, but that's a different story here. This has to do with compressed pointers. Lucene does not run in the same issues like Windows because it has a very larger address space. And swapping algorithms are better. I don't know why, but we don't have the source code of Windows, so we can figure out.